Okay, this video looks at problem 3, and it says it has two parts. Prove the statement if true, otherwise find a counterexample. And this one is regarding the products of even and odd integers. And before we even start this one, it helps to think about the product of integers. I guess I could have written that as a times, sort of a multiplication sign like that. And considering the cases of evens times odds here. And I think if you think about it for a moment, you can imagine that any time you multiply an even number by another number, you're going to get another even number. And so even times even is even times odd is even times odd, or odd times even the other way around is also even, and only the case where we have both odds is the product odd. And so the product of two integers is even if and only if at least one of them is even. That's a true statement, because in all cases where we have the product being even here, at least one of them is even. Okay? And so that's a true statement. For part B, the product of two integers is odd if and only if at least one of them is odd. That's a false statement, because saying at least one of them is odd could include the case that one is even and one is odd. Okay? And that case does not yield a product that is odd. Okay? If we wanted part B to be a true statement, it would be the product of two integers is odd if and only if both are odd. Okay? So we're going to see that part A is true, part B is false, and part A is an if and only if statement. And I'm supposed to remember to do this in layer 2. Part A is an if and only if statement, and so let's do that one first. Let's let P be the statement that the product of two integers is even. Okay? Product of x and y is even. And let's Q be the statement that at least one of x and y is even. Okay? And I need to prove, if I can make quote marks, it'll help. And I need to prove that P, if and only if, Q. Okay? And so I need to do step 1, show that if P, then Q. Okay? And to start with the product being even is very similar to one of the earlier examples here. To start with the product being even is not going to help us too much, and so we're going to prove the contrapositive. That is, if not Q, then not P. Okay? And so I'm going to assume that we don't have at least one of them being even. So we assume not Q and show not P. Okay? And if we assume not Q, then not Q is the statement that if Q is at least one of them being even, then not Q is they're both odd. X and Y are odd. And so hence, so we're going to let not Q be true. Okay, hence there exists an A, which is an integer, such that x is 2a plus 1. We're assuming they're both odd. And there exists a b, which is an integer, such that y is equal to 2b plus 1. Okay. Once we assume they're both odd, then we can move forward and say then x plus, oh, it's the product now. The product, x times y, is 2a plus 1 times 2b plus 1. What am I trying to show? I'm trying to show that not p. In other words, I'm trying to show that the product is odd. If it's not even, it's got to be odd. And I think that's going to fall right out of here when I do this. It's 4ab plus 2a plus 2b plus 1. And go ahead and get out a piece of scrap paper if you need to do the algebra on that. What I'm going to do is I'm going to take the first three terms and factor out of 2 and get a 2ab plus a plus b. And there's nothing I can do with the 1. It's still going to be out there. And that's why the product is odd. So this is 2 times an integer plus 1. Okay, so hence x, y is odd. Okay? And that's exactly what we're trying to prove, and that is not p. And that is the negation of the statement that the product is even. Okay? i.e. not p. And so we're done because we assumed not q. We said let not q be the case, and we showed that not p was the case. And that proves the statement if p then q. Now let me go the other way. Step 2. It's going to be an awful lot like step 1, if you can imagine. I'm going to show if q, then p. And q says at least one of them is even. So we're going to let q be true, okay, and we're going to show p, that is, that the product x, y is even. Okay? And q is the statement that at least one of them is even. So that has two cases. And the cases are that either case 1, just one of them is even. We have one even and one odd. And case 2 is that they're both even. Notice that Q is a statement that at least one of them is even. That could include both of these cases, one of each and both even. So I have to deal with both cases. And case 1, let x and y have one of each. Let's let x be even and y be odd. Okay? And that we can do that without loss of generality. We don't have to consider the other case where x is odd and y is even. Okay? Then there exists an a in the integers such that, let's see, x is the even one. X is equal to 2a. And y is the odd one, so we have a b such that y is 2b plus 1. And what am I trying to show here? I'm trying to show that the product is even. Okay? Well, I'm going to go ahead and form this product. X, y is 2a times 2b plus 1. And I'm going to simply rewrite that as 2a, or 2 times the quantity 2ab plus a. And I'm going to say that this is of the form 2 times an integer, and hence x, y is even. And that's exactly what I'm trying to prove. I'm trying to prove that the product x, y is even. Now I've got to do the second case where they're both even. Okay? And so in case 2, Case 2 is that both are even. Then there exists an a, which is an integer such that x is 2a and y is 2b. That exists a b, an integer such that. Hence, xy is 2a times 2b, which is twice 2ab, which is of the form 2 times an integer, and hence xy is even. Again, what we were trying to prove when we started here, we're trying to show that if Q then P, let me make this a little bit more distinctive here, if Q then P, P was that the product is even, and so I'm done with this one. I guess I'll do part B in another video. Hope this video helps.